This video discusses the inner workings of neural network processing. It shows how a network is built, trained, and tested. Function to be approximated. Let's consider the function y, x equals x2 shown in image 2 to 1. However, let's pretend that the function formula is not known and that the function values are given to us by their values at 4 points. Image 2.1. Image 2 to 1 graph of the function. Table 2 to 1 shows the function values at the 4 points. Table 2 to 1 function values given at 4 points x, f, x, 1, 1, 3, 9, 5, 25, 7, 49. We want to build a formula, or procedure, that can be used for predicting the values of this unknown function at some arguments, x, that were not given to us. In statistical analysis, such processing is called regression. To be able to get the value of the function at points that are not given, we need to approximate this function. When the approximation is done, we can then find the values of the function at any points of interest. That's what the neural network is used for, because the network is the universal approximation mechanism. Network architecture. How a network is built. A network is built by including layers of neurons. See image 2 to 2. The first layer on the left is the input layer, and it contains the neurons that receive input from the outside. The last layer on the right is the output layer, and it contains the neurons that carry the output of the network. One or more hidden layers are located between the input and output layers. Hidden layer neurons are used to perform most calculations during the approximation of the function. Image 2 to 2 shows the network diagram. Image 2.2. Image 2 to 2 neural network architecture connections are drawn from the neurons in the previous layer to the neurons in the next layer. Each neuron in the previous layer is connected to all neurons of the next layer. Such a network is called a fully connected network. Each connection carries a weight. Each weight is numbered by 2 indexes. The first index is the receiving neuron number, and the second index is the sending neuron number. For example, the connection between the second neuron in the hidden layer, H2, and the only neuron in the input layer, I1, is assigned the weight W121. The superscript 1 indicates the layer number of the sending neuron. Each network layer is assigned a bias. The bias is similar to the weight assigned to a neuron, but applied to the entire layer. When the network processing starts, the initial values for weights and biases are usually randomly set. Typically, to determine the number of neurons in a hidden layer, you double the number of neurons in the input layer and add the number of neurons in the output layer. In our case, it is 1 times 2 plus 1 is equal to 3, meaning 3 neurons. Determining the number of hidden layers to be used in a network depends on the complexity of the function to be approximated. Typically, 1 hidden layer is sufficient for a smooth continuous function, and more hidden layers are needed for more complex function topology. In practice, the number of layers and neurons in the hidden layers that leads to the best approximation results is typically determined experimentally. The network processing consists of 2 passes, forward pass and backward pass. In the forward pass, calculation moves from left to right. For each neuron, the network gets the input to the neuron and calculates the output from the neuron. Forward pass calculation. Here is the forward pass calculation. Neuron H1Z11 equals W111 asterisk I1 plus B1 asterisk 1 H1 equals Z11. Neuron H2Z12 equals W121 asterisk I1 plus B1 asterisk 1 H2 equals Z12. Neuron H3Z13 equals W131 asterisk I1 plus B1 asterisk 1 H3 equals Z13. The previous calculations give us the output from neurons H1, H2, and H3. Those values are used as input when processing neurons in the next layer, in this case, the output layer. Neuron O1Z21 equals W211 asterisk H1 plus W212 asterisk H2 plus W213 asterisk H3 plus B2 asterisk 101 equals Z21. The calculation made in the first pass gives us the output of the network, called the network predicted value. When we train a network, we use the known output for the training points, called the actual or target values. By knowing the output value that the network should produce for the given input, we can calculate the network error, which is the difference between the target value and the network calculated value, predicted value. For the function we want to approximate on this example, the actual, target, values are shown in Table 2-2, Column 2. Table 2-2 input dataset for the example XFX 11395254749. The calculation is done for each record in the input dataset. For example, processing the first record of the input dataset is done by using the following formulas. Input record 1 here is input record 1, neuron H1. Z11 equals W111 asterisk I1 plus B1 asterisk 1.00 equals W111 asterisk 1.00 plus B1 asterisk 1.00 H1 equals Z11. Neuron H2 Z12 equals W121 asterisk I1 plus B1 asterisk 1.00 equals W121 asterisk 1.00 plus B1 asterisk 1.00 H2 equals Z12. Neuron H3 Z13 equals W131 asterisk I1 plus B1 asterisk 1.00 equals W131 asterisk 1.00 plus B1 asterisk 1.00 H3 equals Z13. Neuron O1 Z21 equals W211 asterisk H1 plus W212 asterisk H2 plus W213 asterisk H3 plus B2 asterisk 1.0001 equals Z21. The error for record 1 is as follows: E1 equals Z21, target value for record 1 equals Z21, 1.00. Input record 2 here is input record 2, neuron H1 Z11 equals W111 asterisk I1 plus B1 asterisk 1.00 equals W111 asterisk 3.00 plus B1 asterisk 1.00 H1 equals Z11. Neuron H2 Z12 equals W121 asterisk I1 plus B1 asterisk 1.00 equals W121 asterisk 3.00 plus B1 asterisk 1.00 H2 equals Z12. Neuron H3 Z13 equals W131 asterisk I1 plus B1 asterisk 1.00 equals W131 asterisk 3.00 plus B1 asterisk 1.00 H3 equals Z13. Neuron O1 Z21 equals W211 asterisk H1 plus W212 asterisk H2 plus W213 asterisk H3 plus B2 asterisk 1.00. O1 equals Z21. The error for record 2 is as follows: E1 equals Z21, target value for record 2 equals Z21, 9.00. Input record 3 here is input record 3. Neuron H1 Z11 equals W111 asterisk I1 plus B1 asterisk 1.00 equals W111 asterisk 5.00 plus B1 asterisk 1.00 H1 equals Z11. Neuron H2 Z12 equals W121 asterisk I1 plus B1 asterisk 1.00 equals W121 asterisk 5.00 plus B1 asterisk 1.00 H2 equals Z12. Neuron H3 Z13 equals W131 asterisk I1 plus B1 asterisk 1.00 equals W131 asterisk 5.00 plus B1 asterisk 1.00. H3 equals Z13, neuron O1 Z21 equals W211 asterisk H1 plus W212 asterisk H2 plus W213 asterisk H3 plus B2 asterisk 1.0001 equals Z21. The error for the record 3 is as follows: E1 equals Z21, target value for record 3 equals Z21. 25.00. Input record 4 here is input record 4, neuron H1 Z11 equals W111 asterisk I1 plus B1 asterisk 1.00 equals W111 asterisk 7.00 plus B1 asterisk 1.00 H1 equals Z11. Neuron H2 Z12 equals W121 asterisk I1 plus B1 asterisk 1.00 equals W121 asterisk 7.00 plus B1 asterisk 1.00. H2 equals Z12, neuron H3 Z13 equals W131 asterisk I1 plus B1 asterisk 1.00 equals W131 asterisk 7.00 plus B1 asterisk 1.00 H3 equals Z13. Neuron O1 Z21 equals W211 asterisk H1 plus W212 asterisk H2 plus W213 asterisk H3 plus B2 asterisk 1.0001 equals Z21. The error for the input record 4 is as follows: E1 equals Z21, target value for record 4 equals Z21. 49.00. When all the records have been processed, such a point in processing is called the epoch. At that point, we take the average of the network errors for all records, as in E equals E1 plus E2 plus E3 plus E4/4, and that is the error at the current epoch. Obviously, the error at the first epoch, with randomly initially selected weights/biases, will be too large for a good function approximation. Therefore, we need to reduce this error to the acceptable, desired, value called the error limit, which we set at the beginning of processing. Reducing the network error is done in the backward pass, also called backpropagation. Backpropagation pass. How the network error can be reduced. Obviously, the initial weight and bias values were randomly set, and they are not good, which leads to a significant error for the epoch. We need to adjust them so that their new values will lead to a smaller network calculated error. Backpropagation does this by redistributing the error between all network neurons in the output and hidden layers and adjusting their initial weight values. Adjustment is also done for the layer biases. To adjust the weight of each neuron, we calculate the partial derivative of the error function with respect to the neuron's output. For example, the calculated partial derivative for neuron O1 is, because the partial derivative points to the direction of the increased function value, but we need to decrease the value of the error function, the weight adjustment should be done in the opposite direction. Adjusted value of weight equals original value of weight, eta asterisk here. Eta is the learning rate for the network, and it controls how fast the network learns. Its value is typically set to be between 0.1 and 1.0. A similar calculation is done for the bias of each layer. For bias B1, the calculated partial derivative is, then the adjusted bias is calculated as follows. Adjusted value of bias B1 equals original value of bias B1 eta asterisk. By repeating this calculation for each network neuron and each layer bias, we obtain a new set of adjusted weight/bias values. Having a new set of weight/bias values, we return to the forward pass and calculate the new network output using the adjusted weight/biases. We also recalculate the network output error. Because the adjustment of weight/biases is done in the opposite direction from the gradient, partial derivatives, the newly network calculated error should decrease. We repeat both forward and backward passes in a loop until the error becomes less than our limit error. At that point, the network is considered to be trained, and we save the trained network on disk. The trained network includes all weight and bias parameters that approximate the predicted function value to the needed degree of precision. In the next chapter, we will manually process some example and show all the detailed calculations. However, before doing that, we need to refresh our knowledge of the function derivative and gradient. Function derivative and function divergent. A derivative of a function is defined as follows. Equals where del x is a small change in a function argument. F x the value of a function before changing the argument. F x plus del x the value of a function after changing the argument. The function derivative shows the rate of change of a single variable function f x at point x. The gradient is the derivative, rate of change, of a multivariable function f, x, y, z, at the point x, y, z. The gradient of a multivariable function f, x, y, z, is a product of components calculated for each direction. Each component is called the partial derivative of function f, x, y, z, with respect to the specific variable, direction x, y, z. The gradient at any function point always points to the direction of greatest increase of a function. At a local maximum or local minimum, the gradient is 0, because there is no single direction of increase at such locations. When we are searching for a function minimum, for example, for an error function, which we want to minimize, we move in the direction opposite to the gradient. There are several rules for calculating derivatives. The power rule, UA equals A asterisk UA1 asterisk. The product rule equals U asterisk plus V asterisk. The quotient rule equals the chain rule. This rule tells us how to differentiate a composite function. It states that, where U equals f, x. Here's an example, y equals U8 and U equals x2 plus 5. According to the chain rule. Most commonly used function derivatives. Image 2 to 3 shows the most commonly used function derivatives. Equals 8u7 2x equals 16x, x2 plus 5, 7. Take a quick look at the tables. Image 2 to 3 commonly used derivatives. It is also helpful to know the derivative of the sigmoid activation function. Z equals 1 plus exp z. The derivative of the sigmoid activation function gives us the rate of change of the activation function at any neuron. Summary: this video explored the inner machinery of neural network processing by explaining how all the processing results are calculated. It introduced you to derivatives and gradients and described how these concepts are used in finding one of the error function minimums. The next video shows a simple example where the results are manually calculated. Simply describing the rules of calculation is not enough for understanding the subject, because applying the rules to a particular network architecture is really tricky.